part would be of astrophysics, where we'll be talking about early universe, Big Bang theory. How does a early universe look like, and how does strongly understand what are black holes, gravitational waves, and how could our universe possibly end? And also, the next part would be our career paths in cosmology. In this, I'm going to split the astrophysics into three genres, three different fields. One is theoretical astrophysics, another one is an observational astronomy, and data analytics. And the third part here would be where I answer the prerequisite question. We asked on a registration form with the column where you can ask me question, and I got certain questions that I'll be answering it. And later after that, we'll be having a one-to-one discussion where I'll be answering your query about this talk as well as the general astrophysics field.
Sir, voice is not coming clearly.
Let's move to. Am I audible?
Uh, a small request. Everyone is posting it that the voice is breaking. Is there any problem?
Am I audible?
Yeah, you're audible, but there is some internet issue, I think.
I'm audible to you, Subhash. I'm audible to you.
Yeah, you're audible to myself, but your video is somewhat very blurry, I think so. Can you speak now?
Can you hear me?
Yeah, yeah, I can hear you now.
Hello? Give me.
Ah,
Okay, let me start presenting.
okay. Okay, you can present.
Can I present here?
Okay, okay.
Can you see my slides? Can you see my screen? Hello, Subhash. Hello. Can anyone expand? Can anyone see?
Yes, yes, go ahead.
Yes, sir.
Yeah, sir.
I can.
Okay, very guys, am I audible?
Yes,
Yes, you're
Yes.
audible.
yes, yes.
There is a small technical glitch. Within 30 seconds, he will be back. The thing is, he is very less audible, right? So that I just call him for a technical glitch. So he will be back now. We are really sorry for the inconvenience, guys. We are working to give you the best. Oh, thank you. Great words. Okay, until now, let me welcome everyone. Mansi Parmar, Rudra Patel, Vidya S, Abhik Mukhopadhyay, Aditya B, Adrika. Oh my God, more names. I'm sorry. Deva
All right,
Max.
can you hear me?
Yeah, yeah, bro.
Is it clear?
Yeah, now it's clear. Very clear.
Okay,
Perfect.
let me start presenting. As I said earlier, uh, an introduction to the field of astrophysics and the career in the career paths in cosmology is what I'm going to talk about. And for now, I already told you about the different paths where I'm going to talk. One of the basic introduction to astrophysics, in which we'll be dealing with the early theories of the universe, the Big Bang, the how does an early universe look, and how does star form and die, and what are black holes, what are gravitational waves, and how could our universe possibly end, possibly end. I will explain that later why I'm using possibly here. And the second part of our talk would be involving career paths in cosmology, which would be theoretical astrophysics, observational astronomy, data analytics. And the third part would be the prerequisite questions, the questions which the audience have given me previously. I will be answering that. And last part, we will be having some one-to-one discussion about the talk as well as in general astrophysics. So before going to the topic, I want to start with a small story. This is about the American animated show Avatar: The Last Airbender. So this is basically about people in different nations, and each people have certain abilities. They can control certain elements. One can control fire, one can control water, and one can control land. And in a very few people, like one person can control all the elements, and that person is called as Avatar. And this show is about the journey of an avatar named Aang. And in one episode, they will be dealing with, they'll be telling the origin of such powers, avatar powers or bending powers, where they mention a creature called lion turtle, which is an hybrid between a turtle and a lion, basically, and it's the largest creature in that mythological world. It is so large that it can hold mountains. It can people would be living in those mountains, and these turtles give powers to those people. So there are different turtles, and each people doesn't know about its existence. That's why people would be having different powers. And this concept is not original to this Yarbanda show. Uh, this is a very basic concept. Different cultures had such a flying turtle. One such reference can be seen in our Vedic culture, in which Lord Vishnu had taken an uh, Kurma avatar, which is a turtle which holds a mountain in its head. The similar story, similar myth can be seen in a Chinese civilization where the turtle is called as Awu. And Native Americans came up with an independent concept of same thing. I think this was done by Lenape tribe. The Lenape tribe were the huge cosmic turtle holds our entire earth in its back. So why I'm talking to this is how people saw their world. You may ask why they are using a turtle, why there is no another creatures. Because we know that turtle live longer. They outlive most of the humans. They live for hundreds and more than 100 years, which gave them a wise look. That might be one reason why people have chosen a turtle. And to say again is that this type of world is called a disk world. or a flat world. The primitive cultures like Mesopotamian culture or biblical or even Vedic culture believed in a flat earth. And this is because our understanding of nature is based on our perception on reality. And towards our reality would be like what we are seeing. That is the complete earth. The earth surrounding us is flat, and hence it is logical for a primitive people to uh, think that our earth is uh, flat. Still, some people believe that, which is, I don't know why they do, why they still hold on to primitive ideas, but this is what their universe would have looked like. And now we'll talk about universe in a general thing. In a general concept, universe is everything that we have experienced or have yet to experience, every matter, energy that is consist inside an universe. So, but this doesn't start out straightly. The first model of universe, as said, was on a flat earth, and the second model, which was started by Greek and Egyptians, which was a geocentric model. It was even Aristotle and Ptolemy has believed in a geocentric model where Earth is the center of the universe. Mind you, here the universe is just the solar system, in which we consider Earth as the center. We humans wanted to be the center of attention always. So that's why we thought we have importance here. So Earth was a center, and the Sun and Venus revolves around Earth, and it was pretty logical for pre-science era or pre-modern science era, where we look at the sky, we can see that Sun moves from east to west. Hence, Earth is look like stationary. Sun is the one that moves. And after later, there comes Copernicus. He proposed the heliocentric model, in which the sun was the center of the universe. Again, I'm saying sun is the center of the universe because till now the universe is considered as the solar system here. There is no, we didn't consider anything outside the solar system. The universe we have known is confined to inside the solar system. So we have a solar system and planets revolving around it. And it takes time to grasp the idea that every star is, we see in the night sky is just like our sun, and there are different planets orbiting around them. They have their own solar systems, and they are accumulated to form a larger structure known as galaxies. And for a very long time, we also consider there is only one galaxy. We didn't consider there are many galaxies here. So this is our galaxy, which is the Milky Way, and you can see our galaxy is a spiral galaxy. You can see the arms around here, extending here. Next, I'm going to tell you about the different types of galaxies you can see. This is Bart's spiral. Spiral is the most of the galaxy you can see. Bart's spiral is varying over a bar in it, and arms extending from the bar, not from the center. In spiral galaxy, arms comes from the center. Irregular galaxies are the galaxies that doesn't have any original shapes, and elliptical galaxies are the elliptical, and lenticular or circular galaxies are much in a circular shape, and peculiar galaxies are that's forming galaxy, that's not a completely formed galaxy. And this picture is like a galaxy cluster, that we are not an alone, we are not a separate galaxy, we are in a cluster of galaxies. Every single light you are seeing here is a galaxy. This is not a star, this is galaxies. Each galaxy would be consisting of billions of stars. So that's how important this picture is. And this picture, mind you, is a very small slide of an entire observable universe. So you may ask me, how does our universe would look like? So I can tell you that how does our observable universe would look like, because we cannot, there's a range how much we can see. We cannot see beyond that. We don't have enough technology to see that. And this is pretty much the map of an observable universe. And this is uh, cosmic microwave background. This is not optical. This is cosmic microwaves. We map the universe in microwaves. So how does our universe would have begun? So the most acceptable theory right now is the Big Bang theory. The Big Bang theory is that there was a sudden burst in the beginning. Before the Big Bang, there was no time and there was no space. There was completely nothing, the complete emptiness or a complete void. There's not even a space and time to exist. And Big Bang gives the rise of an enormous energy, space, time, and which propagated to give us the galaxies and the universe we live in. And you may be curious to ask me that how can something came out of nothing? So we are all in our conception that there has to be something to produce something. Something cannot come from nothing. Nothing is just nothing. I can give you a simple mathematical, not a mathematical, just an abstract idea like zero. You can consider zero. Zero is nothing. Yeah, separate entity and empty entity. There's nothing inside zero, you would say. But I would tell you that zero has infinite elements into it. In fact, zero has the entire real line into it. You can have a -1 as well as a +1. Together, it would give you zero. And as well as -2 and +2, it would give you again zero. And same with the rational numbers or addition numbers, and it will give you zeros. So in such a way, something can become out of nothing. In our case of universe, if we are having matter, there is an antimatter. When antimatter reacted with matter, it will result in annihilation. So let me tell you more detailed way in the timeline of our big universe. So our universe starts at zero time. Before universe, time doesn't exist. You have to be clear in that there was no before the universe. Before the universe, time was just zero. And it started, and within 10 to the power minus 43 seconds, the universe expanded in a very exponential state. We call this as inflation and also as Planck epoch, because 10 to the power minus 43 is a Planck time. It's the lowest time we can measure. And after that, 10 to the power minus 32 seconds, the universe was very hot and the temperature is 10 to the power 27 degrees Celsius. This is the quark era where the universe is filled with energy as well as quarks and electrons. And as time passes at 10 to the power minus 6 seconds, the temperature has been reduced and it is 10 to the power 13 degrees Celsius. And quarks have started to join together, produce protons, neutrons here. And between 10 to the power 6 and 3 minutes, the formation of nucleus, not a stable neutron, stable elements, but stable atoms. Nucleus has been formed here, like a proton or a helium. Nucleus has been formed. So, at only at the year 3 lakh years, that the universe was 10,000 degrees Celsius. Only here we get our first stable neutral atoms, the first stable neutral atoms formed. Before that, there were nucleus. Nucleus existed before that, but we don't have enough, enough temperature, enough lower temperature for the electron to be binded with the the nucleus. So this era has given us our first atoms, and which atoms created to form an interstellar cloud. So after we time travel a bit, we would be coming at 1 billion years ago. The universe has pretty much cooled very lowly. It is below minus 200 degrees Celsius. Here the clouds of interstellar clouds starts to accumulate together to form the first stars. And 15 billion years later, the universe is at minus 270 degrees Celsius. Here, galaxy clusters are bounded together, and we have heavy elements, and stars die. Many things happen. This is our present day universe. And next, we will be seeing how does a early universe would have looked like. Not in a very early universe, like after interstellar cloud, before the stars. So imagine these things are dust. There was no stars here, so there won't be any bright spots here. Just consider this is how our universe would have looked like without those bright dots there. I'm going to show you other space nebulas, stellar nebulas here. So again, imagine this background without those dots. This nebula is called as a Eagle Nebula because it looks like an eagle. And nebulas are basically nursery for new stars. New stars form a nebulas. I will explain you in a bit how a star is formed and how formed star dies. So, in a stellar nebula, how does a star form is that due to gravity, the dust or gas molecule starts to accumulate, and due to friction, they starts to build up heat. With enough gravity, with enough density and heat, it will be possible to trigger a nuclear fusion into it. Only if a star attains nuclear fusion, it will be called as a star. Without the nuclear fusion, it is just some failed star or a protostar. And a star is separated into two categories as average star and massive star. And this division is based on their mass. Average stars are stars with those mass less than 3 solar masses, and massive stars are basically higher than 3 solar masses. And they use hydrogen as a fuel. Uh, they combine 4 hydrogen molecules to produce a helium molecule, helium nuclear. I'm sorry for molecule, it's an element. So what happens is after a certain time period, the hydrogen fuel runs out, it has to burn helium, and then it moves to another fuels like carbon, and it stops at element iron, ferrous. We call it as a star killer because it cannot fuse beyond iron. So at that point, there would be severe disruption in its hydrostatic equilibrium, and star starts to grow. And star starts to grow in the sense it starts to grow in its size but not in its mass. The density of the stars becomes very less. It starts to grow, but its mass doesn't increase here. Only its size has grows. And this two stars, massive stars and average star, goes through the same phase where the average star would be just a red giant, but the massive star goes into a supergiant, which is very much bigger than the normal giant. And after this, what happens is that there will be a small burst in an average star, what we can call as a helium flash or a helium burst, which will result in a planetary nebula. Don't confuse this with a stellar nebula. This is a planetary nebula. And the remnant of such an explosion would be white dwarf, which is basically iron core. And it is white because it was so hot that it emits light in all wavelengths. And with as time passes, it would start to cool down, and the light would be shift from blue to red. But in terms of massive star, here's something interesting happens. Here there won't be a helium flash or helium burst. It's a very bright burst. In fact, it's the most powerful burst in the entire universe. It was so powerful, and the brightness was so high that you can see a supernova even with naked eye in daytime. And a remnant of such a supernova remnant would be a neutron star and black hole. And the distinction between two depends on their length as well as their spatial radius. So black holes. This image has been taken from the movie Interstellar. But this is a fictional black hole, but this was the most accurate black hole picture that ever came in a movie. So here the same this picture is also from the same movie. Here you can see a dot inside. This is the black hole, and surrounding the black hole there is a light ring. here the light actually bends around the black hole. Okay. So black holes are basically uh, regions in space which are very high in gravity. Even electromagnetic waves such as light cannot escape from it. Hence, we cannot see what is inside a black hole. We cannot see a black hole. I want you to keep this picture in your mind. We are going to in your mind. We are going to see this again. So this is the black hole image. This was this. I think you have all heard the news in last year. We have released the black hole image. This is the first black hole image that we have observed. This predicts what we have seen. Prediction. This is how black hole looks like. And interesting about the star is they what that they actually do while working in the movie. So again, I'm telling you, there's a dark region here, which is the black hole, and surrounding the black hole, there is the photon sphere or a light ring. If you see here, you can again see that dark region, which is a black hole, and again a photon sphere surrounding it. And this image is a work of 2 years, and countries. We have a telescope. Telescopes was placed in 7 different countries, and we gathered information from all those telescopes, and we processed those data to produce such an image. So the data was very high. The data size was 5 petabytes, that it cannot be transferred via internet with the highest bandwidth. So it has to be physically transferred from US to Germany. Here's the scientist Cathy Roman with the hard disks here. So the next topic is the gravitational. We'll be talking about gravitational wave in detail at the end of the talk. I'm just giving you a basic idea here. Like waves like what you have seen in a pond or in a river when you throw a stone in it, the waves are ripples in the pond surface which will travel towards the shore. In the same way, gravitational waves are the ripples in the space-time fabric itself. This was first predicted by Albert Einstein in his work General Theory of Relativity in 1916, where he predicted that accelerating masses are compact objects, heavy masses we are talking here, compact masses, when they accelerate, when they move, they actually create distortion in space-time, which is the ripple effect or the ripples in space-time. And events which would create such black holes or, sorry, not black holes, gravitational waves or accelerating or rotating black holes or rotating neutron star or two black holes orbiting each other, two neutron stars orbiting each other, or a black hole and a neutron star merger, or a supernova or a colliding neutron stars. These powerful events create a distortion in a space-time which would send ripples in space-time. So far we have seen how does our universe started and how it traveled and how does a star forms and how does a star end. Now we will be seeing how could our universe would end. There are different theories explaining that. I'm going to talk about top 3 hypotheses here. One is a big freeze. So the basic idea of a big freeze or big chill is that in a very distant future, the universe would approach 0 Kelvin, which is an absolute zero. This happens because at certain point, all the stars in our universe would end up dying. There won't be enough mass or enough fuel to emit energy, and they will result in either a in a white dwarf or a black hole or a neutron star. And black holes start to accumulate each other to form a massive black holes, and these black holes with given time will evaporate while releasing Hawking radiation. Hence, after a certain time period, the universe would be there won't be any energy left in the universe to be emitted. So, it will be resulting in a very cold and phased out universe. And the next concept here is the big rip. The big rip concept arises with the invention, with the discovery of dark energy or discovery of accelerating expansion. So, I have to tell you another story here about Hubble. When Hubble started to uh, observe the universe, observe the galaxies, he starts to notice that the light that we are receiving from galaxies or stars has a certain bit red shifter to them, uh, which basically means that they had a Doppler shift to them. And Doppler effect is basically what is when wave is moving towards us, its wavelength is bit longer, and when it is moving away from us, its wavelength would be shorter. In the same thing, the Doppler shift or Doppler effect was applied to sound, but it can also be applied to light and any other electromagnetic waves as well. So what we are saying is that the lights are redshifted; they are moved towards the red spectrum, which means that those stars or galaxies moving away from them. And this happens in all the direction, not in a particular direction. Hence, we can conclude that the universe is expanding. So, at a certain time, the expansion is based or expansion is caused by dark energy, and which is pretty much low right now, but we can predict that dark energy can increase, can go to infinite, where it would start to increase the space between the stars or galaxies or even between molecules to strip down everything to its an elementary part. And the big crunch is the opposite of big rip, where the dark energy ends up being zero. In big rip, we assume that dark energy goes to infinite. In big crunch, the dark energy goes to zero. Without dark energy, there won't be any expansion, and gravity takes over, and it starts to accumulate masses together, and it starts to attract other stars, other masses, and towards the end, it all comes back to where it started, to a singularity in a single point. So these are the top three or most uh, possible outcomes we can have. We can have some other theories also there, but these are most possible we can take. So that would end us, and that ends our part one. Now we are going towards the part two, where we will be discussing about career paths in cosmology. Cosmology is in astrophysics. There are three major disciplines you can take, which is theoretical astrophysics, or observational astrophysics, and another one is a data analytics. Data analytics is not to say it's a part of astrophysics, but data analytics is used everywhere in astrophysics. So, in terms of theoretical astrophysics, what we do is that we give a mathematical model, we predict mathematical background to explain certain astrophysical phenomena. And these phenomena include like the formation of a star, formation of a solar system, or black holes, or the accretion disk around it, or quasars, or black hole jets, or even explaining the nature of dark energy, dark matter, or to primordial conditions of our galaxy, like the first black holes, or what happened before the first black holes, before the neutrino era. And the observational astronomy, this observational astronomy is a bit cooler than astronomy because with big instruments here. So here's an example I'm showing you. This is an Andromeda galaxy, which we are seeing in a visible spectrum. At the far left, you can see the same Andromeda galaxy in a radio spectrum. Here, if you notice, the center is dark, but the surrounding the center, there are some bright sources of radio waves here. And then again in the infrared spectrum is basically heat spectrum. So if there is a bright region you can see here, which means it emits more heat there. And the center is very bright here. And even in our visible spectrum, the center is very bright. And the same way as we move to ultraviolet, the center is also bright here, which means the center is emitting more light there, more energy there. Also, X-ray. In an X-ray spectrum, also you can see the center has a very big, it's a very bright spot there. So we can conclude that there is something in the center of the galaxy which gives us such big energies in all spectrums, except radios. Even it emits, you can also see quasars, which are gamma ray bursts coming out of a black hole, center of a galaxy. So we can conclude that there is a black hole inside a galaxy. At the center of a galaxy, there is a very supermassive black hole. And it's not just limited to Andromeda, it is applied to all the galaxies. Even our Milky Way has a huge supermassive black hole at the center of its galaxy. So what else we will be doing in observational astronomy is that we will be using gravitational lensing to look at dark matter or any other heavy mass anomalies there, and we will be sources of gamma rays and also spectroscopy. Observational astronomy does a lot of spectroscopic analysis where we analyze the spectrum, the absorption spectrum or the emission spectrum to conclude the consistency of the materials or elements present in an interstellar cloud or in a star or in a planet. So observational astronomy has, you can deal with much in observational astronomy, like it also divides, you can go for a radio or you can just work in optical range itself. And these are the observatories in India. The first one is the Devasthala Optical Telescope, which is the, let me tell you that this is the largest single mirror telescope in Asia. And Gurugada Radio Astra Observatory and GMT. GMT is one of an, this is also the largest radio telescope, and GMT along with GRO works as an array of telescopes here. And Gervais Observatory is in Pune, and IAO is in Hanley, and Kodaikanal Solar Observatory is dedicated its research towards the solar activities. And Uti Radio Telescope, and there's a Weinberg Observatory in Velu, and Udaipur Solar Observatories in Udaipur. And there are plenty more observatories there, and these are the most important observatories or most largest observatories here. And data analytics. As I said previous, data analytics has been a key important part in astrophysics now. It is both as well as in theoretical as well as in observational. In fact, observational mostly dependent on data analytics. So in theoretical, we will be working in simulation where we need where we give data inputs to produce a template solution. And as I said previous, data science is used to analyze the spectroscopic data as well as gravitational waves. So this is LIGO, Laser Interferometric Gravitational Wave Observatory. This observatory detects gravitational waves. I don't know whether you remember or not. On 2016, we detected the first gravitational wave about 100 years later, since Einstein has proposed it. So how does a gravitational wave work is that when a gravitational wave, that a ripple passes through space-time, it would squeeze and stretch the space-time itself. So any material, when it passes through, would be stretched and squeezed. And this interferometry is basically based on Michelson interferometer, which you would have studied in your UG or in your 12th standard. So this has two arms, each with 4 kilometer, and a laser input, and a photo detector, and a beam splitter in the center. What happens is that the light from the laser has been splitted here. It moves to one end and another end, where it gets reflected by both sides, and which would be detected in the photo detector. In a normal circumstance, there won't be any time delay between both arms. But when a gravitational wave passes through this, the one side of an arm would be stretched and another one would be squeezed. I will pause the slide for a moment and I will show you certain images. I will tell you how it is happened. First, let's see. So this is how a black hole gravitational wave propagates. If you can see, the amplitude here is very high, but as it moves, the amplitude decreases. So it would be very faint that we cannot actually, it's very faint that our instrument should be very sensitive to detect those waves here. And this is what we say, a merger or an orbiting two compact objects. It can be either two black holes or two neutron stars, or even one black hole and one neutron star. And here is a working of LIGO interferometry. So if you are seeing here, you can see that one arm is stretched while the other is squeezed. If this one is stretched, this one would have been squeezed. So there would be a time delay between both lights in a photodetector. With that, we can say that we have detected an anomaly. We can detect the gravitational waves here. And if you check my next slide, this is the data we have got in both LIGO Hanford and LIGO Livingston. They had two observatories. They both measured here, as well as they have another observatory by Vigro and Italy. So here is I will explain this graph. That this spot is what we call as a spiral. Before that, the gravitational wave what we have detected is came from a merger of two black holes. So what happens here is that the black holes starts orbiting each other, and that would take years. And when they are close enough, there would happen a ring down where they starts to merge, and that merger will happen within seconds. And that would give us a peak amplitude here. And after that, there will be a complete silence. If you look closely here, you can see a yellow line inside here, as well as a blue line inside here. So that is our template. That is our theoretical model or our simulated model. And the spikes with noises here is the data or the signal we got. And this is not just the one signal. We would be getting numerous signals. And we have to cross-check every signal, or we have to emit the noises there, and we have to check everything to find a particular template there which fits our curve. So I'm going to show one more video here. So this is a merger of two compact objects. If you see, it starts to merge, but this takes smaller time. It starts to rotate slowly, but when they are approaching closer, the wave's amplitude has become larger and larger, and the merger happens within minutes. And after that, there was a complete silence. There was no more gravitational waves here. I'm showing it again here. See the amplitude of the waves here. So look at the wave here. It's very high when the actual merger happened. Then there was no gravitational waves here. After the merger, there was the space-time was silent after that. It returns back to normal. But the wave starts to propagate. The wave would be traveling throughout the entirety of the universe. The other gravitational wave observatories we have known as the LIGO. One is at Hanford and Livingston, and Virgo. This is in Italy. Both of them are operational, and the Cogra is in Japan, which is built and it is not operational yet. It should be operational by end of this year or next. And LIGO India. LIGO India has signed a partnership with LIGO to have our own gravitational wave observatory, which should be built by the end of 2023. And LISA will be built at the end of 2034. And the LISA is a very important observatory here because we are planning to have an observatory in space, like, and it's an observatory with 3 arms, with each arm of the length of 300 kilometers or 3,000 kilometers. So we have plenty of time for a LISA. So what I'm trying to say here is that in LIGO India, they need, there's an opportunity for data scientists there, people who can analyze data there. But in terms of LISA, LISA doesn't have an observatory right now. There's a lot of opportunity for theoretical work there. So if you are a theoretician, if you want to be a theoretician, the LISA is the one which you have to aim for. And the LIGO India is much for a more data analytic person. And career in astrophysics, what kind of careers you can have in astrophysics after finishing astrophysics is that research scientist. You can be a scientist in any institute, or you can be a teaching faculty in a university. You can be a professor, or you can do a industry job. You can you are from a mechanical background. You are not from a theoretical background. You are from a mechanical background. You want to do something. You could build telescopes for observational astronomy, or you can build rovers, you can build probes, you can build drones that could work in space. So those kind of industry jobs you can go for. Bachelor's in astrophysics, like pretty much there is no bachelor's degree in astrophysics. IIST has given Indian Institute of Space Science and Technology dual degree, which is an integrated degree in which you will be having your bachelor degree and you will be given an option to take astronomy or astrophysics in your master's. Osmania University, Andhra University and Punjabi University say they provide BSc astrophysics or astronomy, but I couldn't find their syllabus in their websites. So I'm not sure about this, but Osmania University do provide a course in masters. They do provide astronomy course in masters. So now masters in astrophysics, you can have an IIST, again Indian Institute of Space Science and Technology, Indian Institute of Astrophysics, Indian Institute of Science, and IUCA, Inter-University Center for Astronomy and Astrophysics, Delhi University. Delhi University and Pune University doesn't give you masters in astrophysics. Rather, they give you courses in astrophysics or astronomy. You would be doing your physics major, but you would be having 1 or 2 papers in astrophysics. So, PhD in astrophysics in India, before saying about the institute, I have to tell you that many institutes give PhD in astrophysics. That actually depends on your guide and the institute. So one of the top major institutes are Indian Institute of Space Science and Technology, Indian Institute of Astrophysics, and National Center for Radio and Radio Astrophysics, and the TIF, Tata Institute of Fundamental Research, provides PhD in astrophysics. They also provide summer projects for master students. You can do one project TIF with, and here is Aryabhatta Research Institute of Observational Science. And ISER is not a complete throughout space science institute, but it's a general science institute. ISER provides multiple courses, with astrophysics being one of them. Again, it depends upon your supervisor and particular institute you choose. I think there's around 6 or 7 ISER. And ICSP Indian Center for Space Science, as well as BITS Pilani also giving you PhD in astrophysics. Also, IIT also provides PhD in astrophysics, and you can check with your supervisor. That depends upon the IIT you are choosing. And these have their for PhD you can have so engineering students could clear GATE or NET to go into the institute or to go for other process. And certain institutes have their TIFR has their own entrances. So it depends upon the institute. But basically you have to clear either GATE or NET. So now for around the globe, the institute where you can do astrophysics, either it can be masters or PhD. One is the Massachusetts Institute of Technology, MIT, Harvard University, Stanford and Princeton, Caltech, California University of Technology. And Lancaster University provides theoretical work, and Fermi Cosmic Physics Center provides both theoretical as well as observational work, and Indian Institute of Cosmology and Gravitation in Portsmouth provides theoretical work, and Institute of Computational Cosmology. This is more like a simulation-based, more theoretical-based institute. And in the International Institute for Physics, as an International Institute for Physics, they provide for various disciplines, with theoretical astrophysics as one of them. And Max Planck Institute of Gravitational Physics also provides theoretical work there. Before going to discussion panel, I want to discuss about the pre-registered questions what we have. So the most common questions what I received was how much being to astrophysics. Doing it, you want to pursue an astrophysics. So for them, what I want to tell you is that look for summer projects in different institute, AIF or IAA provides summer school, summer projects. Do that. Your supervisor right to make them or that clear your because astrophysics is a you want to be and the second one is that you can go for integrated PhD in TIFR or IUCOM. Well, you need to clear just entrance and the respective entrance of their institutes. And some universities like JNU or Delhi universities offer a master's program for they can also and then astrophysics and you this is more masters go for masters then And another question I'm getting is how to become a
Excuse me, sir. Voice is breaking, sir.
Gautam bro,
My
the
voice is
voice is
breaking.
breaking.
Hello?
Yes, bro.
Yes, sir.
Your voice is breaking slightly now.
What about now? Is it clear?
Yeah, it's okay now.
Hello, sir.
Okay.
Hello, Gautam Siddharth, sir. Hello.
Yeah? Yes?
Could you please send this PPT on my mail ID I have provided on the chat box?
Dear electrical
Okay, I
Guruji,
will send that. I will send that to my girl
dear
today.
electrical Guruji, everyone will be getting the PowerPoint presentation to your
Sir,
mail.
I have provided the mail ID on the chat box, sir. Please take a snapshot of that mail ID of everyone who is providing the mail ID,
Okay, okay.
and
If
Okay,
you
then
okay,
you
send
will
it
okay.
on
tell.
the
Okay. Thank you.
to the questions. Am I clear? Am I audible?
Yes, bro, you are audible.
Okay, fine. Next common question I'm getting.
Okay, Mr. Gautam Siddharth is open for questions. You guys can post your questions and or ask your questions regarding me.
Hello, sir. I'm Karthik.
Yeah.
Sir, actually, which factor or parameter determines the formation of neutron star and black hole, sir? Actually, which distinguishes one from another?
The difference between the distinction. That is what we call as a Chandrasekhar limit, which is a Mach limit.
Okay, sir.
So for a white dwarf, even a white dwarf can become a black hole if its masses are larger than 1.4 solar masses.
Okay, sir.
In terms of neutron stars, the mass should be larger than 3 solar masses.
Okay, okay. Okay, sir. Then I have another question too. Why the element heavier than iron is not produced during I mean, formation of planetary nebula? I mean, a low average mass star, sir. Hello, sir. I can't hear. Hello?
Even in, can you hear me?
Yes.
Yes.
Yeah, now audible, sir. Now audible.
Oh, okay. So even in the heavier mass stars, you cannot get elements beyond iron because the binding energy of iron is very high, which cannot be broken by gravity
Oh,
or a gravitational pressure of star.
okay, okay, sir.
Hello,
Thank you, sir.
sir.
Thank you, sir. Thank you, sir.
Any question?
Hello, sir.
Yeah.
Sir, can you please tell how can an engineering student opt for astrophysics or astronomy courses?
Are you in your bachelor or in masters?
Sir, I'm in bachelor's, third year.
Okay. There are certain universities which offer courses for science for the masters in science and for Delhi universities offer courses for engineers. So you can do MSc physics or MSc. I think Delhi University gives a paper in astrophysics. So you can go to Delhi University or any other university to do MSc physics. Then you can choose astrophysics in your PhD research.
Okay, sir, but the thing is, they require BSc level of either mathematics or I mean physics to go for MSc courses in the respective branches.
Yes,
So,
you also
sir,
need it.
how to मतलब उसके ऊपर काम कैसे करें फिर?
English means English.
हाँ
So
सर, तो
if you want
how
to
to opt
prepare
for that?
for that,
Hmm?
you have to study that on your own because you won't be studying statistical mechanics or in-depth quantum mechanics in PTEX.
Okay.
So
Okay.
in MSc, it's pretty much what they teach you, but you have to put your extra work in there.
Okay, sir.
Any questions?
Any other
So
questions?
I said
Sir,
that
sir, as you can say, there is a nothing before the Big Bang. So, what is the reason for the Big Bang this spot?
okay, but previous end, uh, Ayuka and TIF gives an integrated course for PhD students, integrated course and PhD. So engineering from BTech background can apply there. Okay, now to your question is that we actually don't know what triggered the Big Bang, and we are still finding it out. Next question.
Okay, any other questions? There is questions
Hello.
there in chat box, I think so.
Good evening, sir.
Okay,
Gautam,
you
sir.
can. Okay.
Hello.
Yes,
Yeah,
Gautam, you can
ask me the
proceed.
question.
So, Gautam, sir, I have a question. Uh,
Okay.
we spoke about light bending effect in the class today, right? So,
Yes.
uh, is it galaxy lensing is the same as what you said, what you explained in today's class?
You meant gravitational lensing.
Uh, no,
Yes,
sir.
it's the same. It's the same.
Is the distortion in space and time, is that what causing the bending in light, right? So I wanted to ask if the same principle is applying for the micro lensing effect also, or there is any corrections to be uh, done in the data that we receive from the light. uh,
Okay, there
am I
are
clear, sir?
two types of bending. One is
Hello.
bending due to heavier mass objects like another star or another strong mass medium. But there's also bending in which clearly in empty spaces, and that we conclude is due to dark matter. So there's two bendings happening here. One which we are so sure because of gravitational effect of a larger mass, and another bending is because of dark matter.
Okay, so the dark matter lensing is related to the micro lensing effect. Is that what we are trying to say?
Yes, yes,
Okay. Okay,
yes,
sir.
yes.
Sir, I have one more question. Can I ask that? So I was reading this article about a galaxy cluster named Abel 2384, and today the same thing what you have discussed in class about when two stars collide, and there's the ripple effect we see, uh, and the same concept was seen there. There was the north and south clusters, and there was spotted a supermassive black hole in between that. and there was written that there was a bending of shape of gas bridge. So what is that gas bridge actually means between the north and south cluster of that galaxy?
I actually don't know what article you are referring to. Like written on that. But basically, what happens is there are two galaxies you're saying. They coincide. Galaxies has a supermassive black hole inside them. So those black holes will start to merge.
Okay.
I'm not sure about.
I just wanted to know what is that gas bridge that they termed about the galaxy cluster. What do they mean by gas bridge?
I
So
little I need that article.
okay, sir. Okay, thank you, sir.
Is there any questions in the chat box?
Yes, sir. Good day, Gautam sir.
Okay. Hi.
Yeah, sir, I came across this the word quintessence. I exactly don't know what is the meaning. Like with what I know is it's something like hypothetical form of dark energy, but I'm still not clear about it.
Hypothetical dark energy.
It's the spelling is quint essence.
I don't study it any of that. So dark energy is we actually don't know about the source of dark energy or the nature of dark energy itself. We are
Okay.
still working on dark energy. We are just it's still a hypothetical concept to explain the accelerated rate of our expansion.
Okay.
And I'm not, I haven't the quintessence. We an example. Let me give this example. But quintessence dark energy. Any questions?
So good evening, Gautam sir and Subhash sir. I'm Vishnu, and I have a query.
Hi.
That how exactly is gravity termed in astrophysics? Because like gravity,
I
what
cannot
we
hear you.
usually sir,
Can you be a bit clear?
like how is gravity termed in terms of astrophysics? What is gravity in terms of astrophysics?
Gravity for the acceptable idea of gravity uh, is basically the phenomenon of space time. It's a density space time.
Okay.
It's not space. So it's in that they just move curve, but they and it's we see them as
Okay. Yeah. Thank you, sir.
okay. Then I will be answering the chat box questions now.
Hello, sir.
Hello, yeah.
Hello.
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 Hello, sir.
Yeah. Hello.
Sir, can you please share your email in the chat box so that we could be in touch with you?
Okay.
Please provide your email in the chat box so that we could be in touch. Every
Sure.
question that from half an hour we will share with you, sir.
I just sent it in the chat box.
Sir, hello. It's Anup here.
Please put link in the chat box of that PPT so that we could download it and read afterwards also. Please provide in the chat box, sir.
The PPT hasn't been uploaded in any web, so I cannot provide a link as of now, but we will send the PPT to everyone of you.
Okay, sir. Please provide it in the email, sir. So we will read also.
Oh, okay. Someone else can a data scientist without astrophysics degree work in the aerospace sector? I'm not sure about aerospace sector. Aerospace and astrophysics are different disciplines, but in astrophysics sector you can work as a data scientist. As I previously mentioned, you can work in observatories, you can work in what else? There's in computational physics.
Hello, sir. It's Anup here.
Hello?
Hello.
Hello?
Am I audible?
Yeah, you are
Yes, you are audible.
So my question is, I was doing one course, and NASA provided one app named as DS9, which was connected with Chandra satellite, and it was an open source, which makes us to analyze and to figure out some stars and analyze those data of any of the star, like X-ray source. So. Is any ISRO or India having such apps or somewhat data analyzing tools? Because that would help us in the future to make a data analysis.
Times just globally can figure out
Sorry, sir, you are
in
not audible.
one project was conducted for that.
Sir, you are not audible.
Hello.
Sir, you are not audible yet.
Am I?
No, sir, you are not still not audible. Hello.
Hello.
So you are not audible yet. Hello.
Subhash, am I audible now?
Yeah, you're audible now, bro. I think so. You can cut the presentation so that you can less consume the data. You can just use your mobile phone. Am I audible, bro?
Yes.
Yeah, you are audible.
Yeah,
to
you
answer
can. Was that
question, ICTS has conducted a project. Hello.
Hello.
Yes, bro. Now you are good and audible. Bro, are you there?
Hello, sir. Hello.
Uh, guys, kindly wait. Let me kindly wait in the call because let me call him personally so that he will be back soon.
Okay, no problem.
Okay, kindly wait. Kindly wait. Don't go away. Your
Yeah.
questions will be answered. Don't worry.
Okay.
Guys, he is back now. You can ask the questions. Bro, am I audible?
Hello.
Hi, am I audible now?
Yeah, na.
Yes.
Perfect now.
Oh, okay, fine. So to answer the question, ICTS has offered a project. They did a project last year, not last year. It was way back or 2 or 3 years before, and they are still doing it. It's called RAD at Home, which is basically you get to analyze. You use NASA tool to analyze radio galaxies.
Okay.
So that's one example of a project involving citizens, and there are also other examples, but not in India. But in abroad, they are using those things. Citizen science is
Yeah.
where
Yeah.
anyone in the world can work in citizen science.
Yeah. That's what the S9 also is app. It gives a free research way to analyze the stars, galaxies, and other images also by different means.
Yeah.
Okay. Thank you, sir.
Here, I think
Okay.
the professor's name is Anant Hota.
Okay.
He conducted that RAD at Home project here.
Okay, that data analyzing what I have experienced from these 2 to 3 months. I was analyzing 2 to 3 stars and all just for uh, as I was interested in astrophysics. So it will, I think, will it be helpful for me in the future to be an astrophysics as a data analyzer or anything?
Yeah, of course. You can use that in
Because
your
the
resume.
app,
You can use that to do more projects in summer schools.
because I think that app is of NASA, DS9, Chandra satellite. So I was just want to confirm it out for a CV.
Yeah, you can work as a data scientist. You can use this qualification to do summer projects. You can write to previous experiences.
Okay, thank you, sir.
Okay.
Hello?
Any other questions?
Yeah, so I have this question. So can you hear me? Hello?
Hello?
Yeah. So my
Okay.
question is, since I'm pursuing my mechanical
Yeah, I can hear you.
engineering, what is the scope? Yeah. So my question is, since I'm pursuing mechanical
Yeah, I can
engineering
hear you.
second year, what's the scope for mechanical engineer? Okay.
Okay.
Since I'm pursuing mechanical engineering, what's the scope for a female mechanical engineer in the sector of cosmology?
You want to do mechanical engineering or in terms of you are moving towards physics? You want to
So
be a
I
mechanical
can hear
engineer.
you.
Anna, she says that she's doing her was at bachelor's in mechanical engineering,
Yes, I'm
and she
pursuing
want to
currently.
pursue.
No, no, I understand what she's saying. Okay, there's two options here. You can be a mechanical engineer in space industries. You can build a telescope, you can build instrumentations, you can build rovers or drones, or you can shift from your discipline. You can move from engineering to physics, and then you can do theoretical or astronomical work there. So you are having two options now.
Okay. Okay.
Okay.
Okay. Thank you.
Any other questions?
Sir,
Yeah.
am I audible?
Yeah, you are audible.
I had put my question in the chat box. Actually,
Hmm.
what would be the behavior of time beyond event horizon? I actually wanted to ask.
Okay. Theoretically, theoretically, completely in theoretical sense, time would be zero. There won't be any passage of time beyond event horizon. As you move towards the black hole, due to its high energy and high mass, you will be experiencing time dilation. Time starts to slow down for you. So it starts to slow down infinitely till you reach the event horizon. And beyond event horizon, we don't know what would happen, but we can predict that there won't be any time there.
Sir, means would time be zero or time be infinite?
Time be infinite. The passage of time would be zero. There won't be any time. You won't be experiencing any time there. Or you can also say you'll be experiencing infinite time.
Means, sir, if a person is falling inside the event horizon, he would feel like the person beyond the event horizon hasn't moved, and for the person beyond event horizon, the person inside is not falling. Am I right?
Yeah. Okay. Let me put it in this way that if there are two person, one is falling inside a black hole, another one is in outside seeing what is happening there. For a person who is falling inside a black hole, he would be experiencing time in a very normal way. But for the person who is outside the black hole, who is viewing this event, would be seeing that person as being falling into the black hole in an infinite time. Even after 100 years, he will see that the person is still falling there. Am I clear?
Yes, sir. Sir, just one more question.
Okay.
So, what would be the effect of gravity when somebody is falling inside a black hole?
Oh, okay. For a normal person, that's this thing called spaghettification. You have seen a spaghetti, right? Like noodles. So the if
Yes,
you
sir.
are falling vertically towards a black hole, the gravitational pressure at the top of our head would be very much more than a gravitational pressure at our legs. So we would be spread, we would be like stretched. That is what we call as a spectification. Any object that falls in vertically towards the black hole would be stretched.
Yes, sir. Thank you, sir.
Okay. Any other questions?
Any other questions? There is, I can see. Yes.
Yes.
Hello, sir. Sir, I have a question. Just 2 weeks before, LEGO group found a weird event in a space. They detected some waves coming from interstellar galaxies, where they just predicted that there was a collision of two stars or a black hole, but the mass of the star or that black hole is more greater than as compared to a black hole what we right now predicts or we see, and has the size less than a neutron star or a black hole. So can you more clarify that event?
So like we have a template for everything. We have a template for black hole merger. So the black hole merger would give us a gravitational wave of a certain amplitude, and the same way neutron star merger would also give us a amplitude in a certain wavelength. So in this case, we are not sure which one we are getting, and which is possibly our assumption is it's either a merger between a black hole and a neutron star. We still haven't found that yet. We had actually detected waves from two black hole mergers and two neutron star mergers, but we haven't detected waves from a black hole and a neutron star merger. So this could be done.
Okay.
But also, moving objects, just rotating neutron star can also produce gravitational waves. So there are
Okay.
many objects that can
Thank-
produce gravitational waves.
Okay. Thank you, sir.
Any other questions?
Hello?
Yeah.
Hello? Am I audible, sir?
Yes, you are audible.
Sir, in one slide, the topic was, I guess, how the universe can end. In it, there was big rip, you said.
Hmm.
In it, you were saying that I'm sorry, galaxy or something like they will move away from each other. But I have read it somewhere that Andromeda galaxy is coming closer to our galaxy, like in few billion or million years, we can see it like clearly. So like how like possibility.
As I said, the dark energy we are experiencing now is very weak. Even though the universe is expanding in a bigger sense, there are still objects which are attracted to each other. So dark energy is pretty much weak now. And the big rip is under an assumption that in the near future, dark energy will increase and it might even go to infinite. So, and we are on a collision path to Andromeda, and it would happen probably 100 million years or later.
Oh, okay, sir.
Okay.
Thank you, sir.
Any other questions? Karthik M, Kaushik Gorasia, Manu Maurya, NASA Tech, Naveen Robinson, Namra Kolar, Pavitra T.
Yeah, I have one last question.
Kelupa, it's you can ask.
Yeah, sir. Actually, what are the limitations for an amateur astronomer, sir? Is there anything you can't explore use a tool unlike professional astrophysicists?
For an amateur astronomer, money is the limitation. To be
Oh,
frank, money is the limitation.
okay, sir. Okay, sir.
You cannot do that much research on, you cannot do that much observation on your own. You won't even get your recognitions. You need to be recognized. If you want to do observational astrophysics, astronomy is an observational thing. It's not a
Okay.
theoretical thing. For you can get telescopes. If you want to see if you want to observe what I say, nebula or something, you have to get a telescopes at the rate of lakhs. We cannot afford
Yes.
that much. And these things we are still talking about optical telescope. Radio telescopes are much costlier. You need systems which could process those radio data from radio telescope, and you need to analyze those things. So you need certain skills and certain institutes to do that.
Okay,
So
sir.
amateur astronomy in sense is pretty much limited to optical wavelength itself.
Okay, sir. Thank you, sir.
Sir,
Yeah.
so I've got this last question. Sir, can you please illustrate on Friedman's theory of expansion of the universe?
Friedman's theory or Hubble's theory?
Friedman's, yeah.
Hubble's theory. Like as I said, um, okay, let me start this with Doppler shift. If you are standing in a road and you are seeing an ambulance is passing by you, you'd be seeing a variation in its pitch or frequency when it's moving closer to you and when it's moving away from you. Clear? Am I right? You
Yes,
can experience that
yes.
in a which is known as Doppler shift, which means that when an object or a sound is moving towards you, has a very longer wavelength, and when it moves away from, sorry, when it's moving towards you, it has a very shorter wavelength, and when it's moving away from you, it has a very longer wavelength.
Yes.
This same thing can be applied to light as well. So if white light is moving towards you, you would be seeing it in a little bit violet shade or in a blue shade. If it is moving away from you, you would be seeing it in a bit of a red shade. So which that means that the spectrum has been moved towards either a blue end of the spectrum or red end of the spectrum. This is what we call as a Doppler shift. And in terms of
Yes.
in astrophysics or in our universe, all the objects are moving away from us have been shifted towards the red spectrum. That's why we are calling it as a red shift. And depending upon the redshift level, we can say how far and how fast they are moving away from us. So this phenomenon is not unique to a certain location in space, but it is unique in everywhere. We can, in any direction, we can look at look at a nebula or a galaxy. It is a redshifter, which means that they are moving away from us, and it's not moving because the galaxy just cannot move on its own. It should be either pulled by a very strong gravitational force. Otherwise, the space itself, other explanation is that the space between us and that galaxy has been expanded. So we know that space can expand from Big Bang,
Okay.
and we have an earlier theory predicted that the expansion has been slowing down. It should be slowing down and it should be stopped at some point. But after Hubble's observation, it has been shown that universe has been expanding. Expansion of the universe has been accelerated. So we don't know what causes such accelerations. Yeah.
Huh. Yeah, yeah. Thank you, sir.
Yes.
So, I had a question. So, is the universe is expanding due to dark energy. So, dark matter exerts dark energy. So, what is exactly dark matter?
Dark matter doesn't exert dark energy. Both are different things. We don't know the source of dark energy. We don't know the source of dark energy yet, so we cannot tell anything about dark energy. But dark matter is that what happens here is that we cannot account for the gravity of our galaxies. Our galaxy shouldn't, with the masses in our galaxy cannot be confined under gravity. The masses of an individual star systems and gases and interstellar clouds are very much lower to have a confined shape like a gravity. So if we run a simulation with the known masses, the galaxy just won't form. It just moves away. It just splits up. But we don't exactly know what happened, what holds the galaxy together. So we hypothesized a concept called dark matter, which is a non-interacting matter. It doesn't interact with radio waves, but it does exert a gravitational field. It does give mass. It has mass. So that and dark matter is pretty much everywhere, and it accounts for around 98% of the mass we have known. Clear. So we don't know the nature of dark matter. We can say that they are weakly interacting particles. We can assume they are weakly interacting particles. Clear. There's a thing called
Yes.
WIMP particles. There's one assumption that says dark matters can be a WIMP particle, weakly
Yes,
interacting
sir.
matter particle. Yeah.
Means of we don't know the existence of dark matter, but we have to assume that they exist to so that our galaxy can maintain that
Yeah.
gravitational shape.
Yes.
Okay. Yes. Thank you, sir.
I think it was a great session. Last question. Anyone? I think I think we are in the end of the session. No one asked the question.
Okay. Fine. We can end the
And
session, I think.
yep, thanks a lot, Gautam Siddharth, brother. I'm very
Is there a
grateful to
last
you.
question?
No, no one asked for the question, and I think this is the end of the session. And the next thing is, I'm very grateful to you. Brahmastra Aerospace Systems is very grateful to you for your wonderful session.
Thank you. And I'm
Mm,
grateful to you and Brahmostra also.
thanks a lot. And the next thing is, hope you will be conducting more courses with Brahmastra Aerospace Systems, and let us do great things, brother.
Sure. We will do that in future.
Okay,
We
brother.
will again
Thanks a lot.
collaborate.
Sure.
Okay.
Uh, okay. Thank you, everyone, for being with us for the months. We will be giving you good things for your learning experience, for your bridging between industry and academia. Hope we will be doing it in a great manner soon. Thank you, everyone. The session is going to be ended by now. Thank you. Regards, Subhash. Thank you, na. Karthi, Rafat, are you there?
Yes, bro.
End the session for everyone.
Yeah, I'll take it.
Have you seen the was that okay? He's I have a call. Good. Bye.